from University of Wayne, Nancy France. This title, the title of his talk is Functional Annotation of Proteins Using Domain Embedding Phase Sequence Classification.
Good afternoon, I'm Vishu. I'm a PhD student in India, France, and I'm going to talk about protein function notation, and for that task I'm using a type of embedding to embed the protein sequence. So let's have a look at the protein and the sort of data we have used for our task. That's important to understand the contributions. So proteins are important because they are involved in all the bodily functions occurring in any living organism. So understanding protein means understanding life, understanding diseases, and understanding drugs. And proteins are basically chains of amino acids, and they can come to you as a string of letters representing 20 amino acids. So 20 letters, 20 amino acids, and you have a long string representing a protein. And this long protein sequence can have regions which are conserved across species or across a group of sequence which are domains. Domains are very important because they are linked with the functions. I mean, this is not always true, but most of the cases domains are linked with the functions. There are a lot of exceptions. So proteins can have many domains. For example, here you see the colored regions. These are basically domains, and these domains are functional units having a functional, having a name defined in the literature. So when I say protein, I mean domains are linked to the functions. That means protein has some functions. Proteins are performing a lot of functions in our body, and these functions are basically defined with controlled vocabulary. For example, enzyme commission system, gene ontology terms. So any proteins can have different functions, and these functions can be found in this controlled vocabulary. For example, in this work, I work with EC number prediction, so I will talk about EC with an example. For example, a protein is annotated with EC 3.1.21.4. It has a meaning. I mean, it is controlled vocabulary, so it has meaning. This number is hierarchical. The first digit represents the class. For example, this is hydrolase, and the second digit represents that it acts on ester bonds, and third digit represents it's producing 5 phosphomonoesters, and the fourth digit making it more specific exactly. For example, where it is working type 2 site-specific deoxyribonuclease. So, I mean, this is the way protein functions are defined in the literature. We'll be using these functional terms as labels in our problem. We know what is protein, what is functions, what is domain, so where we can get proteins. UniProtKB is the largest protein database right now and the most comprehensive one. This has 2 parts, the Swiss part and the tribal. The Swiss part is the part where you will find proteins which are manually annotated or automatically annotated and manually reviewed. For example, you annotated with a machine, and then a human expert reviewed the functional annotation. And there is another part which is triple, which contains all the unannotated, unreviewed proteins. So that must be a space of problem because we don't know those proteins, and that space may give us a lot of information about a lot of things happening in our body. So triple is a very important place. So this is a snapshot of Swiss board. So you have a protein, it has a name, there is the bigger name, and then you have the domains that it contains. You have the annotation score, for example, how confident the experts were when they annotated. You have functions. Oh, sorry. Why it's moving so fast? Anyways, so you have the annotations. That's triple. Sorry. And the last one, I mean, the last two columns represents two types of functions: DC number and genealogy terms. So these are the functions we need to associate with proteins. And there is another part which is triple, and here you see you also have the annotations here, but these are automatically annotated, and these are not reviewed, so you cannot trust them. Okay, so these annotations cannot serve the purpose of ground truth, right? Okay, so let's talk about the problem then, why I'm interested in working here. So these two curves basically gives the idea of the race between reviewed and unreviewed proteins. You see, till now, I mean till the last day, I think I checked last day, so it's 560K reviewed proteins. And on the contrary, you have 168 million unreviewed proteins, and each month it's growing exponentially. And manual annotation is expensive, so we need something, some tool to do it automatically. And yeah, so the problem is basically you have n number of annotated proteins and n number of unannotated proteins, and you want to find a feasible way to automatically annotate these nu number of unreviewed proteins using the knowledge found from n number of proteins. It's a supervised machine learning problem. It's a big data challenge because, as you can see, it's a huge data space, although the known proteins are very less. And another problem that has been added to the, I mean, if you're thinking of machine learning, these variable length sequences are always a problem. I mean, you cannot have a vector with that variable length sequence. So that's another problem. Well, so this is basically the problem space. Now I'd like to talk about the state-of-the-art research. I mean, it's not like I'm the first person doing the task. There are hundreds of tools around. It's not possible to talk about every one of those tools, so I will like categorically talk about them. Homology-based approach. Basically, these kind of approaches are sequence-based, and they transfer the functions based on the sequence similarity, which is homology. There are machine learning-based methods. Well, BLAST is the most popular tool in that case. So machine learning-based methods, there are KIDIR and neighbor-based methods. For example, SBM Pro. There are deep learning-based methods, which is growing. The deep learning-based methods are coming like exponentially again. So there are DeepRAID, ECPRAID. There are many other tools, and there are also embedding-based methods. For example, BioBack. They actually learn the embedding from sequence. And there are structure-based methods. So proteins can also, I mean, you can study protein based on their structural information from 3D structure, and cofactor is such method that leverages the information from their structure. And for the structure data, by the way, there is PDB, Protein Data Bank. Rule-based approach. These rule-based approach are right now in action. So when I say that the functions are automatically annotated and reviewed, these functions basically coming from UniRule or SAS. So these tools are being used by EBI, European Bioinformatics Institute, who manage UniProt KD. So yeah, so UniRule basically work with manually defined rules. So they need to define the rules manually. And there is the computational version of UniRule, which is SAS, which uses decision tree. There are network-based approach. So in this sort of approach, they are using protein-protein interaction network, or like cofactor game, or some feature-based protein network. For example, Graphy, which is by the way authored by me. So, well, this is basically a rough idea about what's happening. We can go more details later if some of you are interested. So basically our work is based on embedding. So I will talk about the word-to-word, which is a popular word embedding technique, which is published by Mikola. So there are two types of word embedding. Consider a sentence which is composed of 5 words, WT plus 1, T plus 2, and T minus 1, T minus 2. So now you want to, you have a corpus of such sentences and you want to learn the embedding for these words. So Mikola proposed two different ways to do this. One is continuous bag of word model and another is Skipgram. So for continuous bag of word, it's just like a mirror image of each other. So for the continuous bag of words, the input is the context. For example, you have a window of size C, you are moving this window, you are taking all the words, considering the middle word as your prediction task, and all the other words are your context words. So your input is context, for example here, T minus 1, T minus 2, T plus 1, T plus 2 are the context, and you pass through a single layer, shallow neural network, to predict your middle word, okay, which is WT. And this rounds over your corpus and learn the vectors, embedding vectors. And there's another one, Skipgram, where the input is basically your middle word and you want to predict the context. So this is the two different ways of learning word embedding. And to use this word embedding for any classification task, for example, there is this common pipeline. You have a language corpus, and you use any of these, CBOW or Skipgram. You have this word embeddings, which are nothing but vectors representing words projected in a vector space or numerical space, and then you have this downstream task where you use these vectors. It can be any machine learning task, again, or any nearest neighbor can work here. Well, this is basically the word embeddings in NLP. Well, I talked about the sequences, proteins can be seen as text, a sequence. So, we can build a corpus of sequence, right? We can follow this pipeline for learning sequence embedding. So, that can give you this pipeline. You have sequence corpus, you use CBOW as Skipgram, and then you have word embeddings, and you do your functional annotation task. For example, the task I described you. But there is a problem. The problem is that in natural language processing, the words are significant. Significant units. They have meaning. But in case of biology, the sequence are continuous strings. There is no notion of words, right? So how are you gonna get the sense of word? There are a couple of ways. For example, you can split the sequence into fixed length subsequence, and there is two ways. One is overlapping k-bars. These words are k-bars, so k number of subsequent characters constituting the words. So you have a sequence, and you divide it into k-bars, and you have this sentence, and you embed these smaller k-bars. There can be non-overlapping. In case of non-overlapping, so in case of overlapping, you have a window and you move that window to get your k-bars. And for non-overlapping, there is no window. So what you split. For example, you want to learn three bars. So you split your sequence into three different sequences. In each of the sentence, you take 3 consecutive letters without overlapping. So you take these 3, and then these 3, and then these 3. So this is the way you go forward. And in the next run, you start from 1 letter ahead. And this way you go and you create your corpus. So fine, we have now the words, and we can build our corpus and do other things. Well, there is another problem. The schemers are not biologically significant units like word. So basically, you can embed it, they can work, but that doesn't have any meaning in biology, any meaning that is associated with proteins. So this is basically our motivation, our starting point for this contribution. So what we are doing, I talked about domains, right? So a sequence can be again divided into domains, right? And these domains are biologically significant because these domains link with the functions and they are produced following some biological phenomena. So, our purpose sequence embedding uses domains instead of k-mer or 3-mer or 4-mer. By the way, I need to have another information. So there is always the question that what should be the value of k? I mean, it can be 3-mer, 4-mer, 5-mer. This space can grow, and it's like a huge combinatorial space. So you cannot really try everything and say that 3-mer works and 5-mer doesn't work. So to overcome this problem, we have this solution. You have a sequence corpus, and each sequence is transformed into their domain constitutions. So don't confuse, because here everything is same. It's not same basically. So for each sequence, they have different domain domain constitution. So the sequence corpus is transformed into the domain corpus, and then this domain corpus basically acts as your corpus for the word embedding. So you are embedding domains. That's what is the contribution for this word. And to do the machine learning task, so you split your corpus into training corpus and test corpus. You train the CBOW, continuous bag. Well, we use continuous bag of words because we wanted to use the supervised version of it. So each function, this level, each function acts as WT, whereas a window of domains acts as the context. Okay, so at the end we have the supervised embedding. So you have this embedding, and you use with multinomial logistic regression to build a model. And when you pass your test corpus for this model, you have your predictions. And the result, what I'm going to present, is actually based on the top predictions. So you can have 5 predictions, you can have 10 predictions, but we're considering the most, the top prediction, the highly ranked predictions. Okay? Well, why this information is important? Because the embedding method performs really well with even the single prediction. So you can even extend the task for 3, 4, or 5 predictions. Well, to compare the work with k-mer-based embedding, we also did overlapping k-mers like this. So you have the sequence corpus, you transform them into 3-mer corpus and do the same thing. And also non-overlapping. So you have a sequence, and for each sequence, you create 3 different 3-mer sequence. So sentences. Each of them is annotated with the same function, and then you train your CBOW model again. Okay, so yeah, so that's what is basically our proposed approach with domain embedding. To do the experiment, we use a benchmark dataset. Well, by the way, all the data here are real, because I told you that there is a repository where all the protein data, which are real, coming into, and you can use them. So we used a benchmark dataset published in 2018, just last year. This dataset is called new dataset, and this dataset contains equal number of enzyme and non-enzyme sequences. So our task is to first distinguish the enzyme from non-enzyme, and then for each enzyme we try to annotate them with the appropriate EC number. Yeah, and this is the way they actually curated the data. So I'm not going to detail it. We can talk over if any of you is interested. So for the implementation, we used Fasttext, which is a highly efficient library for learning embedding, for training embedding, which is developed by Facebook AI Research. So to do the work, we first transform the sequence corpus into domains using interpro scan. So there is another tool which uses complex computational techniques like mark chains, hidden marker models, to find the domains, and all the things are available through interpro scan. So we run interpro scan over our sequence corpus, and then we found the domains. And then we did what I already mentioned in the schema. Okay, so for the evaluation metrics, we use precision recall, measure, and also accuracies. So let's talk about the results that we have. This estimation. So we are comparing the result with tumor non-overlap, tumor overlap, and domain embedding. So how to interpret the table? So you have level 0. Level 0 means we are trying to distinguish enzyme from the non-enzymes. And as you can see, the domain embedding works really nicely compared to the KMR-based embedding. For the other hierarchy, for example, the level 1, the first class prediction, so you can see that it's even performed better. So if we go forward, like level 2, level 3, level 4, and as you can see, the performance of KMR-based embedding are going really down, whereas we still keep a good faith over domain embedding. Yeah, so we present here 10-fold cross-validation results. So these results are averaged over 10 run for the algorithm. Yeah, I'm almost at the end of the talk. So what we presented here, a different way of learning representation of the sequence. So we are using some domain-specific knowledge here. We have shown the promising performance for enzyme commission number prediction. And we have used Fasttext, which is a fast, shallow neural network-based word embedding tool. And for the future, we would like to extend the work for gene ontology term prediction. As I mentioned, the function can be also defined with gene ontology. And also envision to do an unsupervised embedding to take care of the hierarchical nature of domain and also the hierarchical nature of the functions, for example, EC and ontology. And to have the complete comparison result in analysis with other tools. I'm grateful to India for supporting this travel and all the research and study. Thank you. I'm open for questions.
We have time for one or two.
With the K-merge, you had three proteins which were one word. But what is the average length of a word in this domain approach? Is it very different? So do you have a
it's very different
size?
So this for the domain is very different.
It's much longer.
It can be longer, it can be smaller, but not trimmer. Now that is smaller than trimmer. That's the point. Basically, trimmer doesn't reflect anything in value. This 3 consecutive character doesn't give any functional unit in a protein. So we have the option to use variable length sequences, and these sequences are already categorized, already having a non-length, so you can use that, right? So our task is to don't bother with these non-significant units, but go for significant units which are domains, and they can be variable in length.
And how many domains are there in the vocabulary? So what's the vocabulary size?
Okay, so there are multiple databases for domains. For example, PFORM interpro scan. For our task, we use interpro database, which is accumulating the domains from many different databases, and there is right now roughly so it's from both. It should be so. For PFORM, it was 16,000. For interpro, it's more than this. I'm not exactly sure about the number, but for PFORM, it was 16,000. It's supposed to be twice or more. So 44 something.
So you used Fasttext. Have you used that only for the embedding or also for the classification?
Yeah, embedding has the supervised one.
So you've used it also for classification?
Yeah, exactly.
Okay, and how do you deal with the fact that Fasttext doesn't rely on the sequence, the timing of each character, it just pulls them together?
Like what? I'm sorry.
It doesn't depend on when they appear, the different letters.
Okay, so it's not actually letters.
Oh,
I told you that it's not letters,
yeah.
but I already have the words. And so when I run the interpret scan, I have the data and I sorted them based on their appearance in the data.
But you lose temporal dependency when you use it.
Yes. It's also important in case of this problem that your domain appear in the right order. So order is important. Okay, so Facebook, the default Fasttext is taking care of, like, I have used 5, window size of 5. So it will take 5 domains. If there is 5 domains, it will take 5 domains. And then it will use the CBOW architecture.
Hey, now let's thank our speaker again. Our next speaker is Eduardo Henrique from Nova University. Please.